Hello students, today we are going to understand how finite difference method can be used to solve Laplace equation numerically. By now you know that partial derivatives can be written or it can be made equivalent to finite difference or they have finite difference equivalence, and this can be used to numerically solve the Laplace equation than analytically. So which is much easier many times. So we can just go through the various finite different equivalents for the partial derivatives. Here fx is shown as the first order derivative of x with respect to the first order derivative of f with respect to x. So fx ij is, you know that in finite difference method the space is divided into equivalent grids, and that such a gridding is shown here, and you can consider this middle point as the ijth point. You can write it is written as xi and yi. So this is the jth point. So the function f at the point I comma j is actually this point. Okay, then I minus 1 j is this point, I plus 1 j is this point. Similarly, j plus 1 ith point is this. Then the function value at I j minus 1 is at this point. Okay, now what is written here is the function first order derivative of f with respect to x at the point I j. Okay, so now according to finite difference equivalent, the first order derivative of the function with respect to x at the point I the jth can be written as fi plus 1, that is this point. Okay, fi plus 1 j minus fi minus 1 j divided by 2h. And what is h? H is the distance between these two grid points. Okay, so these 2 points, the space between these 2 points is h. So thus you can find the first order partial derivative of the function using the next point and the previous point, and we call this as the central difference method. You know that. Now similarly, first order derivative of f with respect to y is this one, and that can be found out using the finite difference equivalent in this way. That is the function, if you know the function value at fi j plus 1, this value, so this minus fi j minus 1, then that divided by 2k, divided by k is the difference in the y direction, distance between the grid point in the y direction. Okay, so that divided by 2k will give the first order derivative of f function f with respect to y. Similarly, the second order partial derivatives according to this method can be written by this, or it can be made equivalent to this, or instead of this first second order partial derivative you can use this equation. Similarly, the second order derivative of f with respect to y is made equivalent to this one. So we can substitute, if you have partial derivative functions or equations with partial derivatives with first order partial derivative and second order partial derivatives, that equivalent variables can be substituted by these equations, and then we can try to solve them numerically. Okay, so first we shall see how Laplace equation can be solved using this finite difference equivalence. So first we shall write the Laplace equation. So you familiar with Laplace equation, that is dou square. If I consider f as the function, dou square f by dou x square plus dou square f by dou y square is equal to, or you know, call this part as del square f, right, and that is equal to 0. So this is a second two-dimensional Laplace equation. Now first we have to see which Laplace equation is what kind of an equation, whether it is elliptic, parabola or hyperbola, that we can just try to find out as per your knowledge. So you know that a function written as a times first order derivative of x, second order derivative, then the second order derivative, so we call it as fxx, plus b into second order derivative of f with respect to x and y, and plus c into second order derivative of f with respect to y, okay, and a function of then x, y, then first order derivative and then the second order derivative. So this is a kind of this, if you have an equation like this, okay, with the second coefficient a, b, c as the coefficients of the second order derivatives, and we can distinguish whether the equation is elliptic, parabolic or hyperbolic using the relation b square minus 4az equal to 0. So as per this equation, if you compare this is the coefficient of second order derivative, the coefficient a, here it is 1. So I can say, comparing these two equations, I can say here in Laplace equation a is equal to 1, then second order derivative with respect to x and y is not there in this equation, so I can say that b is equal to 0, and then c here on comparison you can say it is equal to 1. So if I calculate b square minus 4ac, I can write it as 0 minus 4 times a into c is 1, and this is negative. So this is negative means this is less than 0, which means this is an elliptic equation. So Laplace equation is without any inhibitions, I can say that it is an elliptic equation. Okay. So it was just to out of interest, I tried to find out whether what type of equation is Laplace equation, and now we can try to solve this equation. So you know that this is the equation. You have this two second order derivatives of f with respect to x and f with respect to y, and just substitute this dou square f by dou x square and dou square f by dou y square with the finite difference equivalence, which you have already learned and which you know. So when I substitute this dou square f by dou x square, you will get it as, so that is del square f ij can be written to be equivalent as, when I substituted this for dou square f by dou x square, it becomes fi plus 1 j minus 2 f ij plus f I minus 1 j divided by h square. Similarly, when I substitute for dou square f by dou y square, it becomes f I j plus 1 minus 2 f I j plus f I j minus 1 divided by k square. Okay. So for the simplicity, let me assume this h and k as equal to 0, that is spatially, and say when along the x direction and y direction we take the grid point difference as same. So that is, if I take h equal to k, and then I can solve it further as del square f I j as equal to, when I take h and k common, I can take h square outside, then this equation becomes f I plus 1, and just rearranging you can try it out, f I plus 1, then I am writing f I plus 1 j, sorry, f I plus 1 j, then I am writing f I minus, but so variation in I minus I, I'll take it together, so I minus 1 j and minus 4, there are 2 fij, minus 2 fij and one more minus 2 fij, so that becomes minus 4 fij plus fi into j plus 1, then plus fi into j minus 1, and you know that del square f is equal to 0. Okay. So this is the equation. On observing this equation, you can see that it is a 5-point difference formula. We call this as a 5-point difference formula. There are 5 points involved in this formula, right? So if you want to find out, I can say that it contains the 4 Fij. If that can be considered as the central point, then these 4 points are its neighboring points around the central point, as you can see in this figure. So if I can consider this as Fij, and the other 4 points in the formula is this one, this one, this one, and this one. Okay, so you can find out Fij using these 4 neighboring surrounding points. Okay, so this formula, as I said, it is called as a 5-point formula for Laplace equation, and from this formula I can find out, you know that this right hand side is equal to 0. So I can easily find out what is Fij. So from this I can write Fij as equal to, what if I take Fij to one side, and then if I try to rearrange, I can say it is equal to 1 by 4 times h square is there, 1 by 4 times Fi plus 1 j plus Fi minus 1 j plus Fi j plus 1 Fi j minus 1. Okay, so it's interesting to see that you can easily find out Fij using the 4 surrounding adjoining points. Okay, now what you do is to evaluate numerically the solution at the grid point, you apply this formula, and then you get a linear equation. So if I want to find out Fij, or whatever with information what you have, with the information what you have, I can write a linear equation for Fij, right? So if I can write using the 4 adjoining points, I can find a linear equation for using this formula. Similarly, to another next point, I can again use this finite difference method, or using this equation for another grid point, I can formulate another linear equation. Now for another point Ij, I can formulate another linear equation. So with such a system of linear equations at the pivotal points Fij, then you can solve iteratively or using the direct method. You can either use direct method if it's easy to solve, or you can use some iterative methods to solve the system of linear equations and then find out the values of this function at the various grid points. So this is how you can solve the Laplace equation using the difference method, okay, or using the finite difference method. So with solving a problem, where you can easily find out or you can easily understand how this method is applied onto practical cases. So thank you very much.